In this video, I'll be going over the solutions to Codeforces round 634. So starting from problem A, this problem is really just about finding a pattern for the small cases. So if we already given the answers for 1, 2, and 3 in the sample input. So for 1 and 2, you don't have any possibilities. For 3, you can choose 1, 2. For 4, A is greater than B, right? So 2, 1. For 4, we have one possibility. You can choose 3, 1. And for 5, we have 2, and those two are 4, 1, and 3, 2. And then we can go on. 6 has 2, 7 has 3, 8 has 3, and so on. And then we notice a really simple pattern here. This is just, the answer is similar to the floor division of n divided by 2, except that we subtract by 1 first. So yeah, you can check that this formula works for all of the cases described here. So yeah, this is the formula that we use for answer. For problem B, again, we'll just work through small cases. So I think the easiest case to start with is when A is equal to B. So let's say that A is equal to 5. If A is equal to 5 and B is equal to 5, then we can use this construction. And this will go on and on. So this will work for any string of length n. And then for our substrings of length A, we'll have these substrings. And you can check that for each substring, we have exactly 5 distinct letters. So this works. And then let's move on to when B is equal to 4. And in that case, what we can try is we can use an extra A at the start. So then the first substring will have exactly 4 distinct letters. Then we want to choose our next character. And since we want the next character should be the same as one of the characters before. And like we notice that for B equals to 5, we have this pattern. So maybe a pattern also works for B equals to 4. So maybe we can just add the same, repeat the same pattern over and over again. And maybe it'll work. And in fact, it does. So if you see the next substring of length 5, it also has exactly 4 distinct letters. And we can check this for all substrings. Then B equals to 3 is not much different either. We'll just add an extra A. And then it'll look like this. So the conclusion is, in the first part, we have A minus B plus 1 A's. And then in the last part, we have B minus 1 distinct letters. And for the code, it's pretty simple. So first I create the string S, which is the pattern. The pattern consists of A minus B plus 1 A's and then B minus 1 distinct letters in the back. And then we just create a string of length n with the pattern. Yeah, with the pattern repeated over and over again. Yeah. Okay, so for problem C, the second team, which is the team which consists of the students with the same skills, we should always choose the second team from the sizes with the maximum frequency. So here what I do is I input all of the sizes and then I calculate the frequencies of each of the sizes using a map. And then I loop through all entries of the map. And I store the max count of any size in this variable MC. So this variable, this count will be the will be the element that we should use for the second team. So in order to check if a certain X works, we have a few cases. So let's say that so let's choose our team of size X first. Let's choose our team. Let's choose our second team first. So our second team will be the element with the maximum count. So if the element with the if the count of that element is exactly X, then that means that we have one less element to work with. So the size of the map stores the number of distinct elements. But if the element with the maximum count has exactly X occurrences, then that element will disappear from the set of sizes. So we subtract from 1 to find the new number of distinct counts. And then the first team will consist of students with distinct skills. So, distinct skills. So, we need to make sure that the number of distinct skills is greater than or equal to X so that we can form the first team. And so this is the first case if the maximum count is equal to X. The second case is if otherwise we need to make sure that the maximum count is greater than X, because if the maximum count is less than X, then we can't form the second team. So we need to make sure that this is true. And if the maximum count is greater than X, then we can still use this element in the first team. So for example, in this case, what we do is we use X is 3 and we use there are the total of 3 distinct elements, but after we put the 3 threes inside the second team, we can still use a 3 in the first team. So in this case, when the count is greater than X, we just check that X is smaller than or equal to the number of distinct elements, which is the size of the map. And then if it works, then we set the answer to X. Right, D is a very funny problem. It has many approaches, but the simplest one is, so we want to make sure that each row contains 2 equal elements. Each column contains 2 equal elements, and each 3x3 block contains at least 2 equal elements. So what we can do is we'll just turn every 2 inside every single occurrence of the 2 into a 1. And this works because firstly, there are exactly 9 elements, which are 2 in the grid, so we'll change at most 9 elements. And we want to make sure that these 3 conditions are satisfied when we change the 2's into 1's. So each row contains at least 2 equal elements. Well, before, each row has a 1, 1 and 1, 2. So if we change the 2 into 1, then we're guaranteed that we'll have 2 1's. And then the same thing happens for the columns and the 3x3 blocks. So so that's why it works. So the code is really simple. We just input the grid and then we change each 2 into a 1. Okay, for E, I'll just move on to the hard version. So since the maximum value of an element is really small, there are only 200 different values, so I'll iterate over all pairs A and B, and I'll check all of them. So this is what I do here. I just have a double nested for loop. Then if A is equal to B, then the answer is just the occurrence of that element inside the array. So I take the number of occurrences of A inside the array, and I subtract by 1 because I add n to the back of each occurrence. Okay, and then what I do is I'll ignore all of the all of the other elements except for a and b. So in this case, for example, if I set a equal to 1 and b equal to 2, then I'll create a new array which only consists of ones and twos. The elements ones and twos. So this 3 will disappear. So in over here, I used 2 pointers to create the new array from the occurrences of a and b. And if I have an occurrence of a, then I put a 0. Otherwise, if I have an occurrence of b, then I put a 1. And then lastly, after I have this array of zeros and ones, I just I call this solve function, which will, and this solve function will solve the problem for the given that the array only consists of zeros and ones. So maybe like this. Okay, and so for example, let's see. For this array, if a is equal to 1 and b is equal to 2, then what will happen is our original array, the a's turn into zeros, the b's turn into twos, turn into ones, and then all the other elements aren't added. So this will be the new array when a is equal to 1 and b is equal to 2 for the first array in the sample input. Okay, so after we have this binary array, you want to find the maximum 3 blocks palindrome of this binary array, given that the a is the 0 and the b is the ones. What we'll do is we will iterate over x. So initially x is 0, and then s will basically be equal to y in this case. So it'll store the number of b's inside the prefix and the suffix. So yeah, so at first we take the answer will be updated with a maximum of s and answer, and then we try to increase x. And when we increase x, we need to find another a for the prefix and another a for the suffix. So that means we need to find another 0 and another 0. So first we start from the left, and then we look for a 0 and we find a 0 here. So we finished already. And then also, initially s is equal to 3 because there are 3 ones in the array. Then we start looking for a 0 from the right. So we go through the last element, but it's a 1. And then since it's a 1, this array in the middle now only has 2 ones. So we subtract 1 from s. And then we try to find the 0, so we go again. And this time we pass through 0. So now we can stop. And now we have a 3 block palindrome where the prefix and suffix both are 1. And inside it's 2. So let me show the code here. So BL and BR represent if we found a 0 on the left and right side yet. So L and R will store the pointers of put the pointers here. So while L is less than or equal to R, if the element is 0, then that means I found it, so I set the Boolean value to true. Otherwise, it's a 1, so the number of ones inside this range decreases by 1, and I subtract 1 from s. And I do the same thing for R. And then if we can't find another 0 from the left or the right, then we need to break. But otherwise, we have a 3 block palindrome which has x, s, and x. So we update the answer with 2 times x plus s. Yeah, this is pretty much it. Okay, lastly, for f, the first thing you need to realize is that each cell, we can model this as a graph problem, and each node in our graph has an out degree of exactly 1, which means that this graph is a functional graph. A functional graph basically consists of connected components. So maybe like this. Then each connected component has exactly one main cycle. And then in addition to the main cycle, each node in the cycle, so these nodes are the nodes in the cycles, could have forests coming out of them, that have trees coming out of them. So something like this. So this is an example of a functional graph where where each node has an out degree of exactly 1. So our grid here will be in the form of a functional graph. So notice that we can consider each connected component independently. So yeah, so that's what we'll do. We'll solve for each connected component independently. And we want to make sure that when the robots make an infinite number of moves, they won't end up in the same spot. So notice that when the robots make an infinite number of moves, maybe the robots start here, but then after a while, all robots will end up on this cycle, and no robots will be here. So the maximum answer we can have for a single connected component is the length of the cycle. So for this connected component, we can have at most 4 robots because the cycle has a size of 4. And for this, we can have at most 3 robots because the cycle has a size of 3. And in addition to finding the maximum number of robots, you also need to find the maximum number of black cells occupied by robots. Okay, so what we'll do is each one of these nodes in the trees actually corresponds to a node in the cycle. So for example, and we can find the node which it corresponds to by the depth. So for example, this node corresponds to this node over here, because if you think about it, like if we have robots over here, then after one turn they will both be here. So that's why these two nodes are the same, and then these two are the same. So basically, if we number the nodes in the cycle, then basically, let's say that the size of the cycle is C, then we'll number a node with D mod C. So where D is the distance from the node to any node on the cycle. So if we set this as our main node, then this will be 0, and then this will be 1 since it has a distance of 1. This will be 2, these two will be 3. And then this will be 2. These two will be 3. And then this will be 0 because we're taking mod C, and C is 4 in this case. And then this will be 3 and this will be 0. So out of all nodes with the same number in this connected component, we can only take one of the nodes. So out of these 3 nodes, which are all labeled 0, we can only take one of them. And out of these 5 nodes, which are labeled 3, we can only take one of them. So now our job is, after we find the numbers on these nodes, after we find the connected components, we need to use a DFS to find the distance for each node. Then we can number each node. And after we number each node, for each number, we will count the number of black cells with that number. And if the number of black cells is positive, then that means then we'll add 1 to our second answer. Okay, so I'll show the code right now. So at first I'll input C and S. I create the adjacency matrix. So for this adjacency matrix, so in order to find the distance, I actually reverse the edges in the graph. So from U, and then I have this function next, which gives the next node in the graph. So I have this map here, which stores the directions and the vectors. And then next basically given the string in the input, it will give me the next cell of the current cell U. So I basically add these edges from V to U, and then from the next node to current. So I basically reverse the edges and create the adjacency list. And then for each then I loop through each node. And if the node has not been visited yet, then I'll visit it, and I'll basically process the connected component, and I'll visit all nodes. So first I clear the cycle. DFS1 will basically find the cycle in the graph. So DFS1 basically finds the cycle. It's a pretty standard DFS variant, so I won't explain it too much. And then after I find the cycle, so the first answer increases by the size of the cycle. And then the vector A will store the number of black cells with a specific number. So after that, I run DFS2, and DFS2 will find the distance to each node, and it'll also add to the number of black cells for each number. And lastly, I loop through all numbers, and if a certain number has a positive number of black cells, that means that for that number we can choose a node which has a black cell. So we add 1 to the answer, and yeah, that's it. So if this was helpful to you, then be sure to like and subscribe. And if you have any further questions, you can always go on the Discord and see if and discuss with other people. Yeah, thanks for watching.